All right, students, today we're going to be looking at 6.1. And 6.1 covers a lot of review content, so anything that you see that you have already learned or you remember, feel free to skip. We're going over specific properties of exponents, how to multiply them together, and what exponents do when you have common bases being multiplied, and dividing, and all different kinds of things. So you should know the drill by now. You should write the title. You should write the title 6.1, and chapter 6 is about polynomials, and I will give a disclaimer right now. Students find that polynomials are either their most hated or most annoying chapter out of the entire year, or the most difficult. Basically, nothing good. No positive feelings towards polynomials, I don't think. And I also don't share positive feelings towards polynomials in general. But properties of exponents I like, though. So, I mean, there's that. So let's go ahead and get started. So I'm going to break down these exponent properties pretty well, and I'll explain exactly why they are the way they are, and I'll explain in multiple ways how they're true or why they're true. So let's go ahead and start with these names, man. They're like so many convoluted names, and they make sense, but they're not good. There's like the product of powers property, the quotient of powers property, the power of powers property, the powers of quotient properties, and I'm not really concerned with the names of the properties, and I'll never test you over the specific names of the properties. You will have to know how to use them, though. All right, so the first property we're looking at is what happens. Now, actually, before I start, let me explain this. So, consider this situation here, where you've got some variable raised to, like some constant raised to a variable power, right? Some b to the x power. This b is called the base, and anything that's being raised to an exponent is considered the base of that exponent. So this is an exponent, and this is the base of the exponent. Now, I'm going to be using this terminology a lot: base, base, base. Right? So expand the following exponent expression. So you've got 2 to the second power times 2 to the third power. Now, if you notice, the base of this first piece here is 2, because it's 2 to the second. You're raising 2 to the second power. Here, it's 2 to the third. So these are both your bases. I've taken a break from video recording for a couple of days, and my handwriting has not improved. It's regressed. Anyway, so because these bases are the same is the reason why this property works. Now, I'll expand because it tells me to, and I think that's a good way to teach it. So 2 to the second power is saying 2 times itself 2 times, so 2 times 2. All right, that represents this bit here. So, whoops, and I hit my pop filter. The 2 to the second piece right here will come right here. That's 2 times 2, right? And then 2 to the third looks something like this, right? It's 2 times 2 times 2. And these are being multiplied together. So what you end up with is 2 times itself 1, 2, 3, 4, 5 times. 2 to the fifth power. And if you look, you can see a connection between the exponents that we start with and the exponent we end with. So, what is that relationship? Well, that's what this property shows. That is to say that if you have common bases raised to exponents, where you are multiplying the bases together, wow, how did this happen? Then, what did I do? Then you add the exponents. So, that is to say, this is the property here. If you have some base raised to an exponent times the same base raised to another exponent, it is equal to that same base where you have added the exponents together, and that is your new exponent. So when you're multiplying bases, you add the exponents. That's sort of like the shortcut, right? When you're multiplying bases, add the exponents. So you get something like this. You get a bunch of things like this. So here's a couple of examples. So here we've got 8 to the third times 8 to the ninth. And here you can see that their bases are both 8, right? Well, what are their exponents? Well, as I take a drink, we have exponents of 3. What is going on here? How am I doing this? Exponents of 3 and exponents of 9. And so all you have to do to get this answer is take the same base, which is 8, and raise it to the 3 plus 9 power. And that happens to be 8 to the 12th power. That's it. And then you'd have a calculator work this out, because I don't want to do 8 to the 12th. That seems like an annoying thing to do. So here, this next one. Now, I have not explained what negative exponents represent. However, the property is still true. We can still take common base, multiplying, raised to exponents. You add the exponents together. So it is 3 to the 12 plus negative 5, which happens to be 12 minus 5. So that is 3 to the 7th. That is not 7. 3 to the 7th power. All right, you guys following along? And if this seems really simple to you, hopefully you skipped over that section. Now, the quotient of a power, again, I'm not concerned with the names of these properties. I'm just concerned with whether or not you know how to do them. So expand 5 to the 4th over 5 to the 2nd and simplify to see property. So we're going to show the property just like we did earlier. So we've got 5 to the 4th. That is 5 times 5 times 5 times 5, right? 5 times itself 4 times. Now, we've got 5 to the 2nd power, and that is 5 times 5. Now notice what happens. You should be familiar with this sort of process. If you have the same thing on top as you do on bottom, those like cancel and make 1. So one of the 5s cancels with one of the 5s down here, and one of the 5s cancels with one of the 5s down here. And as a special side note, this only is happening because we are multiplying everything up here, and we're multiplying everything down here. You would not be able to cancel these things if you were not multiplying. But we are, so we're fine. So what happens is, when these two pairs of 5s cancel, every time you get a cancellation, you get 1 over 1 and 1 over 1. So in the numerator, you've got 5 times 5 times 1 times 1 over 1 times 1. And this is like showing the steps. It's not necessary. Okay, I'm just demonstrating a point. So, and these ones came from the cancellations, right? Well, 1 times 1 is 1, and 5 times 5 is 25 times 1 times 1 is still 25. So you end up with 25. And the relationship here is that if you look, when you cancel the 5s, it's basically just like they're gone, right? And then you just have 5 times 5 in the numerator, and then nothing in the denominator. Or like, if you want to get technical, like a 1 in the denominator, right? So you got 25 over 1, technically. But we're just looking at it as 25, all right? So this property is comparing what happens when you have an exponent on top of so your base raised to an exponent over the same base raised to an exponent. So division, a quotient of two bases that are the same. And what happens is, what is 25? Well, that's 5 to the 2nd power, right? So the idea here is, if you have 5 to the 4th over 5 to the 2nd, what you do is you take the top exponent minus the bottom exponent. And that is what you get as your result, like your resulting exponent on your base. So what happens is, like this is how you write out the power. If you've got some base a to the m power over some base a to the n power, that is just the base a raised to the exponent top minus bottom. So m minus n. The exponent up here minus the exponent down here. And it's as simple as that. Regardless of what the exponents are, so long as the bases are the same and you're dividing, then you would take the top exponent minus the bottom exponent. And I just shortened this to just top minus bottom. So here we both got 6 and 6, so they're the same base. So that means this property works, and that would just be 6, and then top exponent minus bottom exponent. And that would be 6 to the 9th. And that's it. There's your problem done. Now you try this one over here and see what you get. You could be able to just do this in your head. Well, you should get x to the top exponent minus bottom exponent, which happens to be x to the 7th. All right, so let's move on. Let's see what happens when you take a base that has an exponent and raise that to another exponent. Well, what happens is the property is telling us that what you end up doing is multiplying. How does this keep happening? I'm not clicking on the eraser, it's just doing it. I'll have to get that fixed in between lectures. So what happens is when you have a power that is raised to another power, you multiply the two powers together. So when you have a power to a power, you multiply. So hopefully, as we've been looking through this, you have been writing down the explanations of these, which is to say, here you add the exponents together. Here you take the top exponent minus the bottom exponent. And then here you multiply the exponents. So, and I'll explain why you multiply the exponents too. We'll first use the property and then break it down. So we're going backwards from what you have been doing. So here, you've got y to the second raised to the 4th power. So the property says that you take 2 times 4, and that's y to the 8th. And let's explain why that is true. All right, so if you're taking y to the second, raising that to the 4th power, that is saying that you're taking y to the second times itself 4 times, right? So it's the base of an exponent is what you're multiplying by over and over and over this number of times. So it's y to the second times itself 4 times. So that is y to the second times y to the second times y to the second times y to the second, right? And you can further expand this by breaking y to the second into y times y. So it's y times y times y times y times y times y. You get the idea. Times y times y. And how many y's do you end up with? Well, you end up with 1, 2, 3, 4, 5, 6, 7, 8. So it's y times itself 8 times. And that is like a good explanation as to, or a good showing as to why this works. Okay? So, you try this one here. Tell me what you'd get. And you should be able to do this in your head because it's just a simple multiplication. Well, when you have x to the 5th raised to the 9th, when you have a power raised to a power, you multiply your two powers together. And that would get you x to the, well, that is not right, x to the 5 times 9 power, which is x to the 45th power. And that's it. All right. Moving right along. So, next we've got what happens when you have multiple different bases being raised to powers, and then you take those bases raised to powers and raise them to another power. So this is like saying you don't just have like a power to a power, but you have two different things being raised to a power. It's like two different powers to a power. And what happens is, when this is a product, then you can take this exponent and distribute it by like multiplying into the exponents. So you basically distribute, in quotations, because it's not actually using like a distributive property, the power to each base. So let's look at an example here. You've got x to the 5th, x to the 3rd quantity being raised to the 2nd power. So what the property says is that you can take this exponent here and multiply it into this power and this power by presenting it like this: x to the 5th to the 2nd, y to the 3rd to the 2nd. And this goes back to the power to a power property, where you multiply the exponents. So here, you would take 2 times 5 and 2 times 3, and you would get x to the 10th, y to the 6th. And the reason this happens, again, you can keep breaking these properties down to see why, but it happens like this. So we've got x to the 5th, y to the 3rd, right? And that is being squared. That means you're multiplying by itself twice, which is x to the 5th, y to the 3rd, right? So what this gives you is 2 x's being raised to the 5th power each. And what you can do here is the previous property, where you add the exponents together. So this is x to the 10th because you add these exponents, and this one would be y to the 6th because you add the exponents for the y's. All right? So there we have that. Let's move on. Now, these couple of properties are going to come in handy for a little while, and actually for all of algebra, you'll need to know these. And that is to say that if you have some base raised to the 0 power, so long as that base is not 0, the answer will always be 1. So any number that's not 0 raised to the 0 power is 1. Okay, so like 1 to the 0 is 1. 2 to the 0 is 1. 5 to the 0 is 1. 15 to the 0 is 1. All right, so that's the idea here. Now, the negative exponent property. This is one of the things that confuses students the most, and that is how we have defined and represent negative exponents. So first off, think about the idea of an exponent in terms of multiplying by itself so many times. Well, if you do this, what happens is you start thinking like this. Say you've got 5 to the negative 3 power, right? And you'd say to yourself, well, that is 5 times itself negative 3 times. Hopefully you recognize that this does not make sense, right? Like, you can't multiply a number by itself a negative number of times. That's like saying there's such thing as negative distance, which there's not, right? Like, you can't multiply by yourself any fewer than 0 times, right? So negatives in exponents represent something different. Negatives in exponents represent reciprocals, right? They relate to reciprocals. So when you see a negative exponent, if you were to take the reciprocal of the base, the negative sign would go away. The negative sign is basically, it's saying that the base needs to be written as a reciprocal if you want to make the negative exponent go away. So the negative exponent represents a reciprocal of the base. So if you want the negative to go away, you need to take the reciprocal of the base. And the reciprocal, as we were talking about a long time ago, probably, I can't remember at this point, is like that's 5 over 1, right? This is 5 over 1. The reciprocal is 1 over 5. So if you take the reciprocal of the base, the negative sign goes away. So with that in mind, let's go ahead and use this idea. So this should be a negative 7, by the way. So you've got y to the negative 4th power. Well, that is like saying the reciprocal of y, and then the negative sign goes away. All right, and then you still have the 4th power. So the negative sign up here, as an exponent, represents the reciprocal of your y. So it's really, right now it's y over 1, and so it changes to 1 over y. And this is raised to the positive 4th power. Okay? And what this does is you've got 1 to the 4th power over y to the 4th power, which is just 1 over y to the 4th. This is how you would rewrite this with a positive exponent. You can either stop here or stop here. Now, the next example. Here we've got 1 over z, right? And we're raising this to the negative 7th power. So if you want to rewrite the expression with a positive exponent, to make the negative exponent go away, you need to take the reciprocal of the base. So in our case, The reciprocal of the base is, you flip it on its head. So instead of 1 over z, that is z over 1. And to simplify that, it is just z. So the reciprocal of this base is just z, right? And then the negative on the exponent goes away because we took the reciprocal, and so you have to the 7th power, and that's it, z to the 7th. All right. Wrapping things up here, we have a couple of examples, and then we'll be finished. So, how this works. When you have multiple properties here at play, my advice to you would be to simplify the numerator and the denominators separately, and then work on using like the quotient property. So the first thing I do is simplify anything in the numerator and anything in the denominator that you can. But in this example, you can't because you have a 5 as a base, an x as a base, and a y as a base. And none of those are common bases up here. So you can't combine anything. And down here you have the same problem. So since we can't condense any of these pieces in the numerator or the denominator, what you want to do is use that quotient property where if you have a base over the same base, you can subtract the exponents. So this would be 5 to the top minus bottom exponent, which would be 7 minus 5, which is 2. Then you move on to your x's. You've got x to the 3 minus 1, because the exponent on this x is 1 power, so that's 2. And then here, your y's do something interesting. On your y's, this is y to the 1st power, and this is y to the 6th power. So what you end up with is y to the 1 minus 6th power, and that is negative 5. Now you don't want to simplify into a negative exponent. So if you have a negative exponent, you need to make it a positive exponent. And you do that the same way we have been doing. Now, something I'll say is when you get to a point like this, where you've got 5 squared, x squared, and then you flip this, so it'd be 1 over y to the 5th, you can do something else. Notice, these 5 over 2, or like 5 squared is over 1, x squared is over 1. They don't have denominators, so the denominators are 1. And this has a numerator of 1 and a denominator of y to the 5th, right? So remember, when you're multiplying fractions together, you multiply straight across. So this turns out to be all of these numerators multiply together and all of these denominators multiply together. And you get 5 squared, x squared, and then the times 1 does not do anything. And then 1 times y to the 5th is just y to the 5th in the denominator. And there's a shortcut method to do this. This is the simplified version, and much of this could have been shortened. And here is how I shorten it. All right? This method I'm about to show you, I use all the time when I'm working these problems out on my own. So, say I've got the problem. I'll write it out again. All right, so what we do is imagine. This is all about using your imagination to expand these. Imagine that you had expanded 5 to the 7th and 5 to the 5th, okay? So you've got 5 to the 7th, so you have 7 5s up here. And then you had 5 of them down here. Imagine you had expanded them. And then imagine that you canceled everything you could, right? So you canceled 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, right? How many 5s do you have left and where are they? Well, you have 5 to the 2nd because there are 2 5s and they're on the top. So when you simplify this, there will be 5 to the 2nd on the top. Maybe you can be seeing what it is I'm doing here. So next, when you do the next variable, x to the 3rd over x to the 1st, imagine expanding these. So you've got x to the 3rd, x times x over x to the 1st. And then imagine you cancel them. And you can eventually do all this stuff in your head. It's not so hard. And then you've got x to the 2nd because there are 2 x's again, and again they are on the top of the fraction. So once again you have x to the 2nd on the top of the fraction. Now finally, look at y to the 1st over y to the 6th. Imagine you expanded that. That would be y over y times itself 6 times down here. And I need one more. So what happens is, when you cancel these y's, cancel, cancel, what happens is you've got y to the 5th power, or 5 y's times themselves, and this time they're on the bottom of the fraction. So when you simplify this, you've got y to the 5th on the bottom of the fraction. That is how I like to consider these problems. All right? Now, moving on, let's look at this last problem. We'll be done. This is getting to be a longer lesson. I apologize. Like I said, I've not done this in a little while, so I'll try to breeze through it. So I'll try to go through it quickly. So what happens is, we've got, this is the types of problems you can expect to see on a test or something. I think my volume on my microphone's a little loud. I guess you can just turn me down. Hopefully there's not been any distortion or anything. So that would really suck to have to re-record this. Anyway, so here's my advice. When you've got jumbled up stuff between numbers and letters and variables, right? My advice to you is multiply the numbers first and then condense your exponent, or condense your fractions into a single fraction. So here's how I would do that. You want to write this as a single fraction where you take everything times themselves, and like they're like terms. So that would be the 4 times the negative 5 is negative 20. Then you've got your x to the negative 2nd, y to the 6th. So here you add exponents, so it'd be x to the 4th. And here you've got y to the 5th, y to the 1st, and so that would be y to the 6th. You add the exponents. And you do the same thing on the denominator, where you've got the 20 times the 15. Now I'm just going to write this as 20 times 15, and I'll explain why I do this later. I'm looking ahead to the problem. Next, you look at your x's, and that would be x to the 8th, and then there's nothing over here, so that's just x to the 8th. And then you look at your y's. There's no y's over here, there's just y to the negative 9th here. Y to the negative 9th. So, here we go. Now we need to use the quotient property to simplify this. Or imagine expanding, or a third trick I'll teach you here. All right, so you can either use this property here, where you can take top exponent minus bottom exponent. You can imagine expanding them out. This only works with positive exponents, however. You can imagine expanding these positive exponents out and canceling and seeing where they end up and how many there are. And then how you deal, or my shortcut with how to deal with negative exponents is as follows. If you want to simplify negative exponents, so y to the negative 9th, what you can do is take this y to the negative 9th and move it to the other side of the fraction bar. So right now it's at the bottom, you move it to the top, and when you move it to the top, it becomes y to the positive 9. This is like taking the reciprocal of the base and then making the exponent positive. It's the same idea. The reciprocal, if it was down here, it would be on the top, and so you move it to the top, and then the exponent becomes positive. It might be an oversimplification, but this is in basic terms, this is what happens. So the reason I broke this down into just 20 times 5 still is because the 20s will cancel. There's a 20 up here and a 20 down here. All right. So here's what I want to do. First things first, I'll write my fraction bar. The negative sign stays, so that's still going to be negative. Then I'll do this one step at a time. You've got x to the 4th, y to the 6th, and then the y to the 9th, right? Because that y to the 9th moved up. And then down here, your 20 canceled, and so you've got 15 x to the 8th, and the y moved, so it's not here anymore. Now, you can add these two y's together, or the two exponents together, because you have y times itself. So you've got negative x to the 4th, y to the 15th, because you're adding the exponents, over 15 x to the 8th. Wow, this is getting to be pretty long. We're pretty close to being done, though. So now, the very last thing to do is to combine these x's. And so I'm going to do the whole thing where I imagine them expanded. So if there are 4 of them up here and 8 of them down here, then all 4 of these will cancel with 4 of these down here, and you'll have 4 x's remaining in the denominator. So when these cancel, you'd have x to the 4th down here. Basically what you're doing is you're taking away from the exponents until there's nothing left, and whatever's remaining, you would put that in the location it's at, whether it be the top or the bottom. So what happens is you've got negative y to the 15th. I think I've been saying what happens is a lot this lesson. I'm like off my game, I think. And there's your simplified problem. All right, here's your homework. I'm gonna check and see if the audio is too loud. This might be a louder than normal lesson. Anyway, so there's your homework. You guys know what to do. This is the start of chapter 6. It's been 30 minutes. You probably have less time to work on homework than you would have liked, and I'm sorry for that, honestly. But that's that.